Good morning, dear students. Now we are moving to next lecture of chapter number 4, which is differential equation. The point is concept of singular points. Examples of singular points. Those examples are at x is equal to 0, at x is equal to x0, which is x0 is any arbitrary point which is finite, and at x is equal to infinity of differential equation. So to find out singular point of any differential equation, here we are taking into consideration only linear homogeneous ordinary second order differential equation. Okay, so for those differential equations we are going to study here only singular points. Now consider linear homogeneous ordinary second order differential equation of the type. Okay, if we consider general example of linear homogeneous ordinary second order differential equation, you already know what is mean by linear differential equation, what is mean by homogeneous differential equation, what is mean by ordinary, and what is mean by second order differential equation. That is we already studied in our previous lecture. Now if we consider differential equation of the type which is like this: y double dash plus p of x y dash plus q of x y is equal to 0. If we consider a differential equation of this type, here y double dash is second order derivative of y with respect to x plus p of x y dash is first order derivative of y with respect to x plus q of x y is equal to 0. Now if we have differential equation of this type, then only we are going to study singular point of this type of differential equations. First of all, here how to find out whether that differential equation having any singular point or not. For that we have to convert our differential equation in this form. Okay, now if p of x and or and or and slash or q of x remains finite as x is equal to x0, then x is equal to x0 is ordinary point of given differential equation. Okay, what does it mean? We have to take limit as x tends to x0 of p of x and limit as x tends to x0 of q of x. Okay, we have to solve these limits. Here p of x and q of x we have to find out by converting given differential equation in this form. And if limit as x tends to x0 p of x and slash or means what? P of this limit and this limit or this limit. Okay, so here both has to remain finite. Here I think slash or is not there. Okay, here limit as x tends to x0 p of x and limit as x tends to x0 q of x both has to remain finite. If both these limits remains finite, then such point which is x is equal to x0 is ordinary point of given differential equation. Okay, now if limit as x tends to x0 p of x and slash or, so here we have this and slash or, limit as x tends to x0 q of x, okay, is in remains infinite as x tends to or x is equal to x0, then x is equal to x0 is singular point of differential equation. Okay, what does it mean? If limit as x tends to x0 p of x and slash or limit as x tends to x0 q of x, what does it mean? If this or this means out of these two only one remains infinite, okay, or both remains infinite, so in that case such point x is equal to x0 is singular point of given differential equation. Now how to find out singularity, type of singularity of given differential equation? There are two types of singularity. Here we know if out of these two or both these limits remains becomes infinite, then such point is singular point. And to find out type of singularity, okay, to find out type of singularity, we have to take x minus x0 of p of x. We have to take limit as x tends to x0 and limit as x tends to x0 of x minus x0 square q of x. If both these limits, limit as x tends to x0, x minus x0 multiplied by p of x, and limit as x tends to x0, x minus x0 square q of x, if both these limits both remains finite, okay, then then x is equal to x0 is regular or non-essential singular point of given differential equation. If x minus x0 p of x and limit as x tends to x0, x minus x0 square q of x remains finite. Here we have and means what? This and this both has to remain finite. In that case, x is equal to x0 is regular or non-essential singular point of given differential equation. Okay. Now, now if x limit as x tends to x0, x minus x0 p of x and slash or means this or out of these two only one, okay, if this or both remains infinite, okay, in that case such x is equal to x0 point is irregular or essential singular point, okay, of given differential equation. Okay, so here we know how to find out whether that point is ordinary or singular point. If we get singular point, then how to find out type of singularity? There are two types: regular or non-essential, irregular or essential singularity. When x is equal to x0 is irregular singular point if these limits x minus x0 p of x and x minus x0 square q of x remains finite, both these limits remains finite, then such is regular singular point. And out of these two any one becomes infinite, then x is equal to x0 is essential or irregular singular point of given differential equation. Okay, so in this way we can find out type of singularity of given differential equation also. Now here we have taken singular points at x is equal to 0, x is equal to x0. We already discussed at x is equal to x0 how to find out type of singularity. Now for x is equal to 0, we have to put just here, instead of x0 you have to put x0 is equal to 0. So if you take x0 as 0, then limit as x tends to 0 p of x and limit as x tends to 0 q of x remains finite, then x is equal to 0 is ordinary point. And here if you replace x0 by 0, then you can discuss singular point at x is equal to 0. Now singularity at x is equal to infinity is quite tricky. Okay, so that is not in this way, straightforward way. So for that you have to convert this differential equation into another independent variable differential equation. So here we have differential equation, independent variable y, dependent variable is x, so d2y by dx square. So we have to convert this differential in another form. Okay, so for that we are going to discuss singularity at x is equal to infinity. So singularity at x is equal to infinity is quite tricky, that we are going to study now. Procedure is same. Okay, see, now consider differential equation of the form linear homogeneous ordinary second order differential equation that we already studied, which is like this: d2y by dx square plus p of x dy by dx plus q of x y is equal to 0. Now this is linear homogeneous ordinary second order differential equation, and we have to find out singularity of this differential equation at x is equal to infinity. For that we are taking replacement as z, which is equal to 1 upon x. Now see, as x tends to infinity, if we put x tends to infinity, because we have to consider study singularity at x is equal to infinity. See, in this equation z is equal to what? If you put x is equal to infinity, 1 upon infinity. So 1 upon infinity, infinity is a very large number, so 1 upon very large number, so that becomes almost 0. So then z tends to 0. Means what? If x is equal to infinity, z is equal to 0. So if we studied singularity of z at 0, it is like that we are studying singularity of x at infinity. Both the statements are same. Means what? If we study singularity as z is equal to 0, which is same as singularity at x is equal to infinity. Now for that we have to convert this differential equation which is in terms of x into differential equation which is in terms of z. Okay, so to convert above differential equation in z as, so that becomes d2y by dz square. Instead of x we have to convert that variable into z, plus here we get p dash, okay, which is function of x. Okay, but x is equal to what? 1 upon z. See, here we have put z is equal to 1 upon x, so x is equal to 1 upon z. That's why I here said p dash. P dash is not a derivative of p, it is another function. Okay, this function is different from this function, this is not derivative. Okay, into dy by dz plus q dash instead of x. Here we have 1 upon z and y is equal to 0. So we have to convert this differential equation into this form by using this relation between z and x. Okay. So now let dy by dx is equal to, here dy by dx is derivative of y with respect to x. We can write this equation as derivative of y with respect to z and derivative of z with respect to x. See, here we have used chain rule. Since z is a function of x, z is equal to 1 upon x. So we can differentiate z with respect to x. So this dz will cancel each other and we get dy upon dx as on the right hand side dy upon dx. So that we can write from chain rule. Now here we know that derivative of y with respect to z is here and derivative of z with respect to x. If you differentiate this z with respect to x, so what you will get? Derivative of y with respect to z, and here for this if you differentiate this z with respect to x, you will get minus 1 upon x square. But 1 upon x is z, so minus 1 upon x square is nothing but z square. See, if you take z square, so that will become 1 upon x square. So that is the same term we get over here. So this is nothing but minus z square. Okay. So this is equal to minus z square dy by dz. So here we have converted this term dy by dx, first order derivative of y with respect to x, into derivative of y with respect to z. Now we have to convert this term second order derivative of y with respect to x into this form. So for that, so call this as equation 2. Here we have to give this equation number as 0. Okay. Now if we again differentiate derivative of this term with respect to x, so on the left hand side differentiating with respect to x, what we will get on the left hand side, d2y by dx square is equal to, on the left hand side we get second order derivative of y with respect to x. On the right hand side what we will get, now here d by dx of, see, here we are differentiating with respect to x, d by dx of this term, because this is first order derivative. So dy by dx of minus z square into dy by dz. Now again we are converting this operator which is d by dx into d by dz. So for that, if you write this as d by dz, okay, and multiply by dz by dx, see, this dz will get cancelled, and by chain rule this term is nothing like d by dx is nothing but d by dx. See, d by dz will go out and d by dx, and again we know that dz by dx means what? Derivative of z with respect to x, which is minus 1 upon x square, and which is nothing but minus z square. So this is nothing but, this term is minus z square d by dz. So d by dx we can write as minus z square d by dz. So if we put this term here, okay, what we will get? So on the left hand side we get minus z square d by dz. Now this is equal to minus z square into, we have to differentiate this term with respect to z. Okay, So here we have to use product rule. If you differentiate minus z square, so that becomes minus 2 times z, derivative of this term with respect to z, multiply by dy by dz, okay, minus, if you put minus z square as it is, and derivative of y with respect to z becomes second order derivative of y with respect to z square. Okay, now if you multiply with minus z square to this term and this term, so if you multiply with minus z square to this term, so that will become z cube, and here plus z raised to 4. So this is nothing but d2y by dx square. So on the left hand side we have second order derivative of y with respect to x. On the right hand side we have derivative with respect to z. Now call this as equation 3. Now see, in equation 2 we have dy by dx in terms of dy by dz, and second order derivative with respect to x in terms of second order derivative with respect to z. So we can put equation 2 and 3 in this equation to get equation of this form. Okay, now using equation 2 and 3 in equation 0, so put equation 2 and 3 in equation 0, we get, see, d2y by dx square. For that we will get this term, so 2 z cube, okay, multiply by dy by dz, okay, plus z raised to 4 d2y by dz square, okay, plus p of x multiply by dy by dz, and dy by dz is nothing but minus z square dy by dz, okay. Instead of dy by dx we can write this term plus q of x into y is equal to 0. Now we can write this equation as, by collecting all the terms of second order derivative, so d2y by dz square z raised to 4 is the only term with second order derivative of y with respect to z, plus now first order derivative dy by dy by dz, so here 2 z cube, okay, and minus 2 z cube minus here z square p of x into dy by dz plus remaining term is q of x y is equal to 0. Now if we divide whole equation by z raised to 4, so this upon z raised to 4, okay, here z raised to 4, 0 upon z raised to 4 is 0, here we will get 1, okay. Now we get differential equation of this type, see, d2y by dz square plus p dash, which is this term, multiply by dy by dz q dash, which is this term, okay. Now comparing with equation 1, we will get p dash of 1 upon z is equal to, see, p dash is coefficient of dy by dz, which is 2 z cube minus z square p of x. Now p of x, but x is what? 1 upon z. So we can say p, which is function of 1 upon z, okay, divided by z raised to 4, and q dash of 1 upon z, which is q dash, which is 1 up q dash is equal to, which is coefficient of y. So that is q of 1 upon z divided by z raised to 4. Now, these two formulas are very important. So, using these two formulas, we can discuss singularity. How? Now, here you have to take p dash of 1 upon z and q dash of 1 upon z. If you take limit as z tends to 0 and limit as z tends to 0, means what? If you take z tends to 0, z is equal to what? 1 upon x. So 1 upon infinity. So that is nothing but x tends to infinity. Okay. So if both these limits p dash and q dash, both these limits remains finite, then x is equal to infinity is ordinary point, or z is equal to 0 is ordinary point. Okay. And if out of this and or this limit or both remains infinite, then we can say z is equal to 0, which is nothing but x is equal to infinity is singular point. And to find out type of singularity, we have to take z into p dash and z square into q dash. Okay. If this remains finite and this remains finite, then this singular point is regular singular point or non-essential singular point. And if this limit or both remains infinite, then z is equal to 0 or x is equal to infinity is irregular singular point or essential singular point. So we converted this by using this relation. We converted how to find out singularity. Okay. Now, remember, these both formulas are important for solving problems. So as we solve problems, we will get clear-cut idea about singular points, how to find out singular points of any differential equation. So for that purpose, I have written here 3 problems. We are going to solve these 3 problems in this lecture. So with this, theory of chapter number 4 is over. Okay. And only problems are remaining for chapter number 4. So first problem of singular point is that show that point x is equal to 0 is regular singular point of Laguerre's differential equation, which is given by x y double dash means what? d2y by dx square plus 1 minus x into y dash plus lambda into y is equal to 0. Okay. So we have to show that x is equal to 0 is regular singular point of given Laguerre differential equation. So solution of problem number, first of all, write given differential equation, which is x y double dash plus 1 minus x into y dash plus lambda into y is equal to 0. Now we have to compare this differential equation with y double dash plus p of x y dash plus q of x y is equal to 0. Now in this equation, coefficient of y dash y double dash is 1, but here coefficient is x. So we have to divide this equation by x. So if we divide this equation by x, 0 by x, so that still becomes 0. So x upon x is 1. Okay, so here 1 minus x upon x, y dash lambda upon x into y is equal to 0. Now we can compare these two equations. Remember this point. Okay, how to convert this equation into this form. Now comparing, what we will get, p of x is equal to 1 minus x upon x, and q of x is equal to lambda upon x. Now we have to find out x is equal to 0, whether that point is singular point or not. For that, at point x is equal to 0, here limit as x tends to 0 of p of x is equal to limit as x tends to 0, p of x is what? 1 minus x upon x. Now this is equal to, if you put value of x is equal to 0 in this equation, so that will become 1 minus 0, okay, divided by 0. So 1 minus 0 is 1. So 1 upon 0, 1 upon 0 is infinity. Okay. Now limit as x tends to 0, q of x is equal to limit as x tends to 0, q of x is what? Lambda upon x. This is equal to. So again, if you put value of x is equal to 0, so that becomes lambda upon 0. So lambda upon 0 is again infinity. Okay. Now here both these limits are infinite. Then x is equal to 0 is singular point of differential equation. Okay. If both these limits remains finite, then and then only x is equal to 0 is ordinary point. If this limit or both remains infinite, then we can say that x is equal to 0 is singular point of given differential equation. Now to find out type of singularity, at x is equal to 0, how to find out type of singularity? We take x minus x0 p of x, limit as x0 tends to x tends to x0 p of x, which is equal to, now here x0 is 0, so that's why we have to take limit as x tends to 0. X minus x0 means what? X0 is 0, so that will become x p of x. Now that is equal to limit as x tends to 0, x multiply by p of x. So p of x is nothing but 1 minus x upon x. So 1 minus x upon x is equal to, now see, this x will cancel with this x and we get 1 minus x. Now if you take limit as x tends to 0, so we have to put value of x is equal to 0. So that will become 1. See, if you put value of x is equal to 0, so that is 1 minus 0, which is 1, and this is finite. Okay. Similarly, limit as x tends to 0, x square q of x is equal to limit as x tends to 0, x square multiply by q of x, and q of x is what? Lambda upon x. Okay, this is equal to, see, x square upon x, so that will become lambda into x. If you put value of x is equal to 0, so lambda into 0, So this is again 0. So that is again finite. Now here limit as x tends to 0 x p of x and limit as x tends to 0 x square q of x both have remained finite. Okay, so then x is equal to 0 is what? Regular singular point. Okay, regular or non-essential singular point of Legure differential equation. Okay, if out of these two limits any one or both remains infinite, then that will become irregular singular point. Okay, now we are going to solve next problem, which is problem number 2. Procedure is same. See, what is problem number 2? Show that x is equal to 0 is an ordinary point of Hermite differential equation, which is given as y double dash minus 2x y dash plus 2 lambda y is equal to 0, where lambda is constant. Now given differential equation is y double dash minus 2x y dash, okay, plus 2 lambda into y is equal to 0. Now comparing with standard differential equation, which is y double dash plus p of x y dash plus q of x y is equal to 0, we get, if we compare this equation with our standard differential equation, we get p of x is equal to minus 2x, okay, and q of x is equal to what? 2 lambda. Now we have to show that x is equal to 0. Okay, so at x is equal to 0, if we take limit as x tends to 0 of p of x is equal to, so limit as x tends to 0 p of x is what? Minus 2x is equal to, if you put value of x is equal to 0 here, so that will become minus 2 into 0, which is 0, and 0 is finite. Again, limit as x tends to 0 q of x is equal to limit as x tends to 0 q of x is what? 2 lambda. Here lambda is constant. If you put value of x is equal to 0, so again that is 2 lambda. Okay, and this is again finite. Since both these limits remains finite, okay, then x is equal to 0 is ordinary point of given differential equation. Okay, if out of these two limits any one remains infinite or becomes infinite, then we can say such point is singular point, and for singular point we can find out type of singularity by the same procedure we did in our previous problem. Now moving to problem number 3. It is problem number 3. Show that point x is equal to 1 is an ordinary point of differential equation y double dash plus x square y is equal to 0. Now again, given differential equation is y double dash plus x square y is equal to 0. Now comparing with standard differential equation, which is y double dash plus p of x y plus q of x y is equal to 0, we get p of x is equal to, now see here p of x is coefficient of y dash, and in our differential equation there is no term of y dash, so this is 0, and q of x is coefficient of y, which is x square. Now x is equal to 1, we have to find out singularity at x is equal to 1. So at x is equal to 1, limit as x tends to 1. Okay, so here x is equal to x0, x0 is 1. So limit as x tends to 1, p of x is equal to limit as x tends to 1, p of x is what? 0, which is again 0. Okay, so this is again finite, and limit as x tends to 1, q of x is equal to limit as x tends to 1, q of x is what? X square is equal to, if you put value of x is equal to 1, so 1 square is 1, which is again finite. Okay, so hence, since both these limits remains finite, x is equal to 1 is ordinary point, of given differential equation. If out of this or both limits are infinite, then we can say x is equal to 1 is singular point of given differential equation. Okay, now with these problems we stop our lecture over here. In our next problem we will solve remaining problems.